Good morning, everyone. Our team consists of Kevin, Kandyce, Suhani, Maako, Anna, Kay, Conor, and Aaren. Our project focus was on harnessing citizen science around the world to enhance land surface temperature prediction using machine learning models. To begin with context, the prevalence of urban heat islands have been drastically increasing over the last several decades. These areas are classified as having higher land surface temperatures compared to areas that experience less urbanization. While some people enjoy the higher temperatures, animals and our planet don't. This phenomenon can be attributed to the abundance of heat-absorbing impervious surfaces.
Rising heat could lead to a multitude of health issues. Heat illnesses, which are the health issues, can range from mild to deadly, and it is imperative to understand the severity of increasing LSDs and the effect that UHAs have on them. Our research question is can we utilize machine learning model techniques such as the random forest and XGBoost models with citizen science data in order to enhance predictions of land surface temperatures. Our null hypothesis is that incorporating vegetation data from Globe Observer and Collect Earth Online data into the machine learning models will garner no significant changes to the accuracy of the model to predict land surface temperatures. The alternate hypothesis is that adding this data would create greater accuracy of the models.
46 interns in the Earth System Explorers team with 37 locations to use the Globe Observer app. Our group analyzed 958 sites, and we uploaded them to an application called Zooniverse for citizen labeling. We sourced our temperature data for each site from the Landsat 8 satellite. The data was accessed with an open source code to extract LST for June 2024 as a daily mean. Then we used the Collect Earth Online platform to gain additional citizen source data for land cover. Collect Earth Online uses Sentinel to satellite imagery for each site an image was captured.
The graphic on the right provides a summary of our stages of data preparation. Throughout the process, we had to filter out a lot of inaccessible data. For example, many of the photos uploaded to Globe had not yet been processed or were not actually up photos. We were then able to feed this data to two machine learning models, Random Forest and XGBoost. These are the results for our Random Forest model. So we trained three models, one with coordinate data, one with coordinate and globe data, and one comprehensive model with coordinate, globe, and Collect Earth Online data. We then evaluated them with three statistical metrics, R-squared, root mean squared error, and mean absolute error. In summary, we found that Model 2 performs worse than Models 1 and 3, but adding in Collect Earth Online data to Model 2 to create Model 3 enhances the accuracy.
The three XGBoost models saw a similar trend to the Random Forest models. Model 1 was the most accurate model by a slight margin, followed by Model 3 and then Model 2. The addition of Collect Earth Online data greatly reduced prediction error. Interestingly, Globe Observer data actually served as a bottleneck for Model 2's performance. This bar graph shows the features our models use to predict land surface temperature measured using their F-score. F-score is a measure of the amount of times the features used to split data in any tree across the model. Longitude and latitude are by far the most used features, followed by 2 Globe Observer labels and then 3 CAO labels. We can consider the features with the highest F-scores to be the most important in predicting LST.
We were surprised to find that both of the models that used Globe Observer or Collect Earth Online data were slightly less accurate than our baseline models using coordinates. We also found that Random Forest models performed better than XGBoost models. There are a few sources of error that limited the predictive power of our models. Some images were poorly taken and had lower quality compared to the rest, resulting in less accurate labels. Second, our sample size was relatively small, containing less than a third of the possible photos. However, the addition of CEO data improved the accuracy between models 2 and 3.
In summary, we found that there is potentially a strong relationship between land cover and land surface temperature that would become more apparent if we address the sources of error in our study. We know from past studies that vegetation and other data correlate to land surface temperature, as is shown in the bottom right graph. Citizen science may play an important role in capturing this land cover data. Moreover, citizen science is particularly relevant because it encourages open science that could power global change. Further research on this topic is imperative to better understand the complex relationships between citizen-sourced land cover data, land surface temperatures, and urban heat islands.
Our research project was heavily influenced by the guidance of our mentors. We extend our thanks to each of them for their contributions. Additionally, we are grateful to the SEAS team and UT Austin's Center for Space Research for providing the resources necessary to make this project a reality.
These are our student and program reflections.